All right, so in this second video in our tropical cyclone climatology series, we're going to take a look at the necessary large-scale environment conditions for cyclone formation, or what we'll call tropical cyclogenesis here. Keep in mind that these are necessary, that we need them to be there, but just because we have them there doesn't mean that we're going to get a tropical cyclone to form. So in this sense, we call them necessary but not sufficient conditions for tropical cyclone formation. So the first of these is a thermodynamic control. Unfortunately, it's getting a little chopped off here on the bottom right with my camera, but we're looking at a sea surface temperature that is greater than 26 to 26.5 degrees Celsius. So in the top part of this panel in the northern hemisphere, we have the August climatological mean sea surface temperature. We have the January climatological mean sea surface temperature in the southern hemisphere. And these are the months in which tropical cyclone formation peaks within each of the two hemispheres. All of the black dots are tropical cyclone formation locations over a 30-year period. So though this doesn't represent the sea surface temperature when a storm formed, it represents a very clear relationship that tropical cyclones typically form only where the sea surface temperature is sufficiently warm, generally greater than 26.5, 26 degrees Celsius. And that blue line is that 26.5 degrees Celsius climatological isotherm that we see here. There are a few exceptions at high latitudes, in particular in the North Atlantic and the Southwestern Pacific Ocean, but very, very few exceptions to the larger collection that we see through here. So we can ask why? Why do we need such warm ocean waters to have a tropical cyclone form? So the first part is that the warm ocean waters are the heat and moisture source, the energy that fuels a tropical cyclone's winds. We call this enthalpy. It is a combination of heating, so it's related to temperature, and moisture, so it's related to specific humidity here. So as air passes over the ocean, it gains heat and moisture so long as the air is slightly cooler than the underlying ocean surface, it will gain heat. And it's always drier than the ocean surface because the air is very rarely saturated above the inherently saturated ocean. So the air gains heat and moisture from the underlying surface. And as we'll talk about later in this video and in subsequent videos, that energy serves to fuel the tropical cyclone's winds. In addition to this, there's typically a fairly uniform temperature to the tropopause across the tropics and the subtropics. So there's a typical difference between the underlying ocean temperature and the tropopause temperature, which is where the tropical cyclone's air stops rising and spreads out in the form of outflow. The difference in temperature between those two levels governs how much of this heat energy from the underlying ocean can actually go into fueling the tropical cyclone's winds. Not all of it is going to be able to go straight into kinetic energy in the form of cyclone wind, but 30 to 40% of it at least needs to go into that. And this 26.5 Celsius threshold is that sea surface temperature at which you typically get 30 to 40% of that underlying energy from the ocean going into this ability to actually fuel the cyclone's winds. Furthermore, this sea surface temperature value provides a minimum threshold for rewarming the atmosphere. And by that I mean we have antecedent thunderstorms, whether that be with an African easterly wave, a monsoon disturbance, or along the intertropical convergence zone. Thunderstorms form and they warm and moisten the middle troposphere, but the rain that falls out of them evaporates and cools the lower portion of the troposphere, that just above the ocean. So we need that heating from the underlying ocean to be able to rewarm that air. And we need to rewarm that air to get a uniform profile of heat energy within the atmosphere, within the troposphere, to allow for a tropical cyclone to form. We'll talk a little bit more about that as we get into some of the other necessary conditions here. And ultimately, once you have a storm form, especially as you get to a higher intensity, it's helpful to have not just 26.5 degrees sea surface temperature, but sufficiently warm ocean temperature to 25 to 50 or more meters of depth. Because cyclones are just that, they're cyclonic disturbances. And we talked when we discussed Ekman upwelling or Ekman transport, that not only does flow upwell when you have some barrier that causes the water to be directed away from it, but cyclonic circulations also cause water to be directed away from the center. So that's going to bring water from beneath the surface toward the top, and we want that to be sufficiently warm so that when we have a tropical cyclone already in place, it will be able to maintain its intensity even if it's upwelling colder water from beneath. So the first two here really get into the idea of formation. This latter one is really talking about after formation. The second condition is a dynamical control. We need some source of large lower tropospheric cyclonic rotation, or what we would call vorticity. And nominally, this should be away from the equator. Generally, it's at least 2 to 3 degrees latitude away from the equator, although that's not a hard and fast rule. And we want that rotation to increase with time. So in our previous video, we introduced this diagram here, where we had cyclone formation locations in the shaded boxes here. And the black dashed line was the location of the intertropical convergence zone, where the easterly trades converge, or the monsoon trough, as you see here in the western North Pacific Ocean, as well as the southeastern Indian Ocean near Australia. And in most ocean basins, it is these two features, the intertropical convergence zone and the monsoon trough, that give rise to the incipient or predecessor disturbances for a tropical cyclone to form. Whereas in the Atlantic basin, there's not that strong of correlation between that black dashed line for the intertropical convergence zone and where tropical cyclones ultimately form. And that's in large part because they form through other means, as we discussed before. African easterly waves are one source, and we looked at this when we introduced African easterly waves, that we had this wave evolve over the several day period while it was over Africa. And then as it left the coast of Africa, some days later, September 10th and the 11th, it ultimately gave way to a tropical depression, a tropical cyclone in its initial stages. So some easterly waves do this, but not all easterly waves are able to do this. And as we'll talk about in our next lecture, mid-latitude disturbances that extend down over the relatively warm waters of the subtropical Atlantic basin also can serve as predecessor disturbances with large lower level cyclonic rotation for a tropical cyclone to form. So why do we need this low level cyclonic rotation? So first off, we know that that cyclonic feature, especially near the surface, even though we're over water, is directed inward because of the effects of friction. Friction causes air to diverge out of areas of high pressure and converge into areas of low pressure. So we have cyclonic rotation that is spiraling inward toward the center of the cyclone with these features. So this provides a locus around which thunderstorms can form. That low-level convergence provides a source of lift for thunderstorms to form in what is typically a warm and moist environment, as well as to organize. You have individual thunderstorms that rotate around the center and then come together into a single spot near to the center. And that organization is a crucial characteristic of the persistence of an initial tropical cyclone. Secondly, as the rotation rate associated with this disturbance increases, the ability for air either to escape from that area of rotation or enter into that area of rotation from the outside diminishes. And we call this inertial stability. So let's think about it as though we're driving. You're coming up toward a corner and you're going to turn right, for instance, in this case. If you take that turn at 5 miles per hour, you might feel a little nudge toward the corner, but it's going to be just that. It's going to be a relatively small nudge. If you come up and take that tight corner at 60 miles an hour, you're going to feel a very strong nudge toward the corner. It'll probably cause you to shift in your seat like I just did here as you hold on while making that very fast, very tight turn. That's the idea that we're talking about here. That rotation exerts a force that is directed inward ultimately. And consequently, it keeps air that is in there, and it keeps air that is out of there from actually being able to get in there. The faster the rotation, the stronger that force ultimately is. Finally, from a dynamical standpoint, that low-level cyclonic circulation has an initial amount of rotation or vorticity associated with it. If we have a thunderstorm embedded within that area of rotation, there's a strong updraft, vertical motion associated with that thunderstorm. And it can take that larger scale vorticity or that larger scale rotation and stretch it out and amplify it in so doing. So I always like to use a figure skater analogy here. A figure skater is initially going to start low to the ground with their arms spread way out from them, and then they will bring their arms in as they start to rise up to higher heights. As they do so, the rate at which they rotate becomes much faster. Same idea, same principle holds here. Our third criterion is another thermodynamic control, and this is the idea of conditional instability. So the condition for instability to be realized is whether you are saturated or not. Ultimately, this is looking at a measure of CAPE. Though CAPE is not very significant within the tropics in most cases, we do, at least initially, want there to be a small amount of CAPE in order to support initial thunderstorm development. So we have a cluster of thunderstorms depicted here, largely for for illustrative purposes. And then here we have a diagram of what is known as moist static energy, which is related to three things: temperature, specific humidity, and height. And the primary features that show up here on this diagram in our initial depiction, this solid black line here, are the temperature and moisture aspects of it. Temperature and moisture typically decrease as you go upward away from the surface, and so you get this initial shallow layer near the surface where it's fairly uniform, and then you decrease rapidly until you reach to the tropopause roughly here, and then as you cross the tropopause, your temperature increases, and so too does your moist static energy as you continue to go upward from there. So when you have a thunderstorm here initially, it's relatively warm and moist near to the surface and comparatively dry and also cool in the middle troposphere. And what that thunderstorm does is as air parcels come in and then lift along that saturated or pseudoadiabat, there's latent heat release that takes place associated with the condensation. And so we get warming and moistening in the middle troposphere and upper troposphere, but then as precipitation forms and falls out, a portion of that evaporates, and the associated cooling reduces the moist static energy. So after the thunderstorm has formed and rained out, you get this dashed blue line that you see right here as the post-thunderstorm state. You have lower moist static energy associated with the cooling near the surface than you did before in the solid black line, and you have more in the middle to upper troposphere given by this dashed line relative to what you had before, with the black line lying to the left. It's important to get to a state where you have this vertical type of structure, because then if you have another thunderstorm that takes place, you're not going to have this ability to cool or to bring in drier, cooler air from the environment that can then foster evaporation as precipitation falls out. So let's get into that here. So as noted, that conditional instability allows for there to be thunderstorms to develop and to persist. And the thunderstorms play two key roles here. So we talked about how they warm and moisten aloft while also cooling near to the surface. So when you get that vertical profile of moist static energy being fairly uniform with height, when you get a thunderstorm forming, you will have precipitation fall out, yes, but its ability to evaporate is substantially reduced. You have moistened the vertical profile from the surface on upward. And so you do not get this ability to generate cold air that spreads downward toward the surface and then outward in the form of low-level divergence. That low-level divergence disrupts cyclonic rotation. That cool air that comes down near to the surface has to be rewarmed by the underlying ocean in order for the next thunderstorm to be able to form. We need this to occur once to get from that initial state of cold near the surface and warmer anomalously as you go up to one where it's warmer over the entire depth of that profile. So we can't get away with the idea or we can't get away from the idea that thunderstorms will initially warm and moisten aloft and cool near the surface, but we only want that to occur once. We want then the ocean's energy to go into spreading warmth over the entire atmospheric column. We don't want to continually have downdrafts bring cold air toward the surface that the ocean has to warm, then you get another thunderstorm, does the same thing. You want a single thunderstorm to persist without these downdrafts disrupting things. Why? Because once you have genesis occurring, once you have a tropical cyclone forming, those thunderstorms take that ocean's energy and loft it upward or mix it upward within those towering thunderstorms near to the center. So you take that profile, that blue dashed line, and you shift it toward the saturation value that was even further to the right. What that means is you create an area near the center of the storm that has much, much, much higher moist static energy than areas even 100 miles away, yet alone 1,000 miles away. Because that's related to temperature and moisture, that means you've got a very warm vertical column near to the center compared to elsewhere. So you're going to have a lot higher thickness near the center than you will away from there, which means that strong low pressure near to the surface will give way to much higher pressure away from there. And that gives you very strong winds near to the low levels around the center of the storm. If you have cold air infiltrating or dry air infiltrating the storm from outside of there, those thunderstorms will collapse. It'll bring that cooler, drier air in the form of downdrafts toward the surface. Instead of thunderstorms being present there to take the ocean's energy and spread it vertically, that ocean's energy is going to have to go into rewarming that low-level air. And then, and only then, will it begin to be able to spread that warmth vertically and create that large difference between the warmth near the center and that at larger and larger radii, which is directly, again, related to the cyclone's intensity. So this allows us to get into our last two elements here. The first one is our dynamic control of vertical wind shear, the change in the wind speed and direction with height. And I have two cartoons here depicting a low shear case, light easterly winds giving way to light westerly winds, and a high shear case, light easterly winds giving way to very strong westerly winds here. And in this case, these circles depict wind that is coming out of the screen, and X's depict wind that is going into the screen. So we have strong low-level cyclonic rotation giving way to weak upper-level cyclonic rotation in both cases, although the size of the circles is a little bit different between the low shear and the high shear case. So if we view the tropical cyclone as being like a cylinder, essentially, and we have wind acting on that cylinder at different heights, it will lead to that cylinder maybe not being specifically within the vertical. When the wind is light at all levels, and in particular when it's similar at all levels, that cylinder is not really tilted much from the vertical. So that cylinder represents the heating, the warmth associated with the cyclone. And that leads to very strong localized pressure falls. And if we look at the change in pressure from underneath that cylinder to its periphery, it is a very large change over a very small distance. That pressure gradient is very large, which gives rise to a very strong horizontal wind speed. Whereas in the high shear case, with the different winds with height, it tilts that cylinder over. So you spread that heat. If you go upward, you have no heating here, no heating here, and you have a little bit of heating in all of these particular areas here. So that heating spreads out, is not confined within the vertical, and so that spreads out the pressure response at the surface. The minimum is not as low as it is in the low shear case, and the slope of this curve is a lot less steep than it is in the low shear case. And so in general, we want vertical wind shear to be low. In terms of its magnitude, less than or perhaps equal to 10 meters per second, or about 20 knots of vertical wind shear between 850 and 200 hectopascals. Although there's a lot of variability and a lot of sensitivity in there to the profile between those two levels. So in terms of the why, we've already talked a little bit about this on the previous slide, but independent of any other factors, low vertical wind shear magnitudes foster that upright vortex with heating constrained in a small horizontal area to facilitate those localized large surface pressure falls, as compared to the tilted vortex that spreads the heating out over a larger area. But we can't always evaluate this independent of other environmental considerations. In general, vertical wind shear is also associated with cooler and drier air on the outside of the cyclone. We know that the cyclone is relatively warm and moist compared to its surroundings. And so vertical wind shear provides a way to try to forcibly bring that cooler, drier air into the center of the cyclone. When you do that, that cooler, drier air gets into the saturated thunderstorm core, which causes evaporation to take place. And as that evaporation takes place and the precipitation falls out, you reduce the warmth of that core relative to the outer environment. So you weaken the storm, and you need to rewarm that air from the surface on upward. And we'll talk about that a little bit more as we go into our last criterion, which is mid-tropospheric relative humidity. So this is a thermodynamic control, and we want there to be large, lower to middle tropospheric relative humidity. There's not a specific threshold value, but in general, tropical cyclone formation will take place when you have relative humidity 60 to 70% or greater, and all of the other conditions being met. In this case here at left, we have a predecessor tropical disturbance here to the southeast of the Lesser Antilles and to the northeast of the northern coast of South America here. And this yellow and orange shaded region is associated with dry mid-tropospheric air, in this case associated with the Saharan air layer. And we see that clouds are clustered south of that, but as you get further to the north and to the west, clouds are not particularly present. The center of rotation of this disturbance is actually right about here where the mouse cursor is at this point. So you have a lopsided storm where dry air has suppressed thunderstorm activity on the northwest side while not affecting that further to the south and east. Here in the diagram at right, we have two arrows depicted here, 1 and 2. And this is related to the ability for vertical wind shear to forcibly bring drier air, cooler, drier air from the outer environment into the core of a developing or developed tropical disturbance. That first one, the arrow that comes down and then up, I always like to envision like a boxer with an uppercut here, that it brings the dry air into an outer rain band associated with the cyclone. It causes evaporation to take place within that, so it flushes cold air down toward the surface, and that low-level convergent circulation brings that cooler, drier air in close to the center of the storm, which then weakens the extent to which that center is warmer relative to the surroundings, even as surface energy has started to be able to overcome that. Whereas arrow 2 that we have depicted here is like a punch straight to the head, a knockout punch from a boxer. And this is where vertical wind shear is taking cooler, drier air and putting it straight into the center of the tropical cyclone. So it doesn't have to go this roundabout way of getting into the outer part, coming down to the surface, and then being brought in toward the center that way. It just gets straight into the center there. And that has the same effect, fostering evaporation. The cooling associated with that leads to a weakening of that warm column relative to the surroundings, which then requires energy from the underlying ocean surface to be able to rewarm the air and reestablish that difference between the center and the surroundings to maintain or intensify a tropical cyclone. And so ultimately, if we think about this independent of other environmental considerations, if you have high relative humidity, you don't need as much in the way of thunderstorm activity ahead of disturbance formation to moisten the atmosphere in the middle troposphere. We said before that thunderstorms help to warm and moisten the middle troposphere. If you have relative humidity at 10%, you're going to need a lot of thunderstorm activity to be able to moisten it to 70 or 80%. Whereas if your relative humidity is 60%, you may only need one round of thunderstorms to be able to sufficiently moisten the atmosphere. But of course, we can't consider this in and of itself. And we refer to this combination of large vertical wind shear from the environment to the storm and low relative humidity as ventilation. It's just like ventilating somebody with oxygen or ventilating your house by opening up the windows. You're bringing air in from the outside. And the properties of this air are cooler and drier, which fosters evaporation, which mitigates the extent to which the center is warm relative to the surroundings. And it reduces the ability of those surface enthalpy fluxes, those surface heat and moisture fluxes, to increase the intensity of the cyclone. They have to go in, at least temporarily, to rewarming the near surface air before you can then pick up where you left off and try to intensify the tropical disturbance or tropical cyclone from there. So summarizing these points here, surface enthalpy fluxes are the energy that fuels a cyclone's winds. Surface sensible and especially latent heat fluxes as air spirals in toward the center provide the energy source for a cyclone's winds. Thunderstorms are key here. It's not latent heat release within thunderstorms, but it's what these thunderstorms do to take heating from the surface and mix it upward, and then overcome the initial cooling associated with downdrafts there to allow for development of the tropical disturbance to proceed. If you have high vertical wind shear in the presence of low relative humidity, not only are you going to tilt over the vortex and spread out the horizontal extent of the heating that takes place, but you're going to forcibly ventilate the cyclone with cooler, drier air that is going to weaken the extent to which it is warmer than its surroundings, thus requiring those surface enthalpy fluxes to go into rewarming that air near to the center of the cyclone before you can then use it to fuel the cyclone's winds again. We'll come back to this idea of surface enthalpy fluxes and tropical cyclone formation in our next series of lectures looking at tropical cyclone formation, but I wanted to take this opportunity not just to introduce what we need in terms of high SST, strong cyclonic rotation, conditional instability, low shear and high relative humidity, but a bit about why we need all of those elements. We'll come back to more of the why later, but for now, we'll close here and close our series of lectures on climatology by looking at more climatological characteristics of the larger scale environments in which storms form, specifically into the North Atlantic Basin. Until then, thanks for tuning in.